Okay, chapter 16 is about acid-base theory. And you're certainly familiar with acids and bases from 1210 a little bit, but we're going to go quite a bit into more depth now, including different ways to define acids and bases. So the first simplest way to define an acid and a base is called Arrhenius theory. And Arrhenius theory says that when you dissolve an acid in water, that it's going to produce H plus ions in solution. And when you dissolve a base in water, then it's going to produce OH minus ions in solution. That seems really straightforward and just fine. We'll see later some ways that Arrhenius theory actually falls short and needs to be improved upon. But that is kind of the definition of acid and base by Arrhenius theory. All has to do with what a substance will generate in solution when it's dissolved in water. Now, before we get too far into acids and bases, we need to talk about H plus ion. So if you think about it, a hydrogen atom is just a proton and an electron. When you ionize it to H plus, then it is just a proton. And protons, lone protons, are superreactive. If you have an aqueous solution with a lone proton just floating there in the water, it's not going to be very long before it reacts with something, most likely a water molecule itself. And so H plus is convenient. It's an easy way to simplify acid-base reactions, but it's worth taking a moment and realizing that there's really no such thing as H plus ions in water. It's a flagrant lie. What we really have are hydronium ions, H3O+. And I'll take this moment to say that hydronium ions are also a bit of a white lie, not quite as flagrant as H+, but the reality is with water, things get really complicated really quickly, and you'll have clusters of many water molecules that share an H+ between them. You'll get a variety of different structures like that. And hydronium ion just does a good job of adding the right amount of complexity, and it gets the job done very nicely. So we'll write reactions in terms of H plus sometimes, and we'll write reactions in terms of H3O plus or hydronium ions sometimes, and you can consider them completely equivalent to each other. Hydronium is closer to what's actually going on. I will probably tend to use the hydronium ion more, but you can write H plus, that's fine. It's not incorrect, right? So let's talk a little bit about acids. Here we have HCl, and here are the two different ways to write how HCl will dissolve into water. On top here we have HCl dissociating into H plus and Cl minus, but we know H plus is a bit of a lie, and so perhaps a better, or at least a more accurate way to write this would be HCl plus water, and it's going to produce H3O plus, that hydronium ion, and Cl minus. And hydrochloric acid is what we call a strong acid. That means that it ionizes 100% in the water, and this arrow here, the reaction arrow, is just a regular reaction arrow pointing to products, meaning that it will proceed all the way to the products. We'll contrast that in a minute. There are also acids called weak acids that do not ionize completely, and so you put their reaction arrows as these double-headed equilibrium arrows that we've been dealing with for the last chapter. And hydrofluoric acid is one example of that. And again, we can write this with the H+, or we can write it as hydrofluoric acid reacting with water to produce hydronium and fluoride ion. And we've got some nice renderings of what those molecules might look like. A way to think about strong acids versus weak acids is how much of the reaction ends up as products and how much of it remains as reactants. So for a strong acid, we see there's none of the HCl left, and it's entirely in the H3O plus and the Cl minus. Those are the products. That's why strong acids, we don't put an equilibrium arrow. We show that it goes all the way to products. Here's the weak acid, hydrofluoric acid, and you'll notice actually a large majority of it remains in the reactant side of that reactant, HF. And then some small amount is going to go to products, H3O plus and F minus. That means this is a reactant-favored reaction, and the equilibrium constant will be substantially smaller than 1. And we'll deal with equilibrium constants for weak acids in a couple of sections. Now there are 7 strong acids, and you may have already encountered a list like this and maybe started memorizing them, but if not, now is the time to memorize these 7 strong acids. You must know them. So here they are: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. And some textbooks will leave off chloric acid. It is the weakest of these 7, and it's kind of on the border of whether some textbooks consider it strong and some textbooks consider it weak. But we're going to call chloric acid a strong acid. Now there are many compounds that contain hydrogen atoms, but they don't generate free H plus in solution, and so they're not considered an Arrhenius acid. And we can name a ton of these. Methane, CH4, ammonia, NH3, and in fact we'll see that ammonia is a base instead of an acid, which is a little bit strange. Sucrose, that's C6H12O6. We can sit here all day naming compounds that contain a hydrogen, but that hydrogen is not going to react to form hydronium ion in water. So acids are a special class of compounds where they have a hydrogen who has a bond strength that's usually pretty weak, and that if it loses that hydrogen, then the anion that's left behind is going to be particularly stable and things. There are some structural properties that will make something acidic well beyond just containing a hydrogen. And so compounds that do have a hydrogen that will be released in water, making them an acid, they'll usually list that hydrogen atom at the front of their formulas. So you'll notice CH4, C12H22O11, NH3, all of those hydrogens come somewhere in the middle or end of the chemical formula. And our 7 strong acids here, they list their hydrogens at the beginning. That's just a convention to sort of signal and communicate that this is an acid and that it has 1 hydrogen that it's able to give. Or in the case of H2SO4, 2 hydrogens that are able to be released in the water. Now, under the Arrhenius definition, remember, a base is something that's going to generate OH minus in solution. And the strong bases are a really boring group. They are ionic compounds that are soluble with hydroxide as the anion. So sodium hydroxide generates OH minus not by breaking and forming new bonds the way that acids do when they transfer a hydrogen over to the water. But instead, it's just the solvation of sodium hydroxide. The hydroxide ion was there from the beginning, and when you put it in water, it's released and it goes out into solution. So the group 1 and the heavy group 2 hydroxides are soluble hydroxide. And what we mean by heavy group 2, if we look at the periodic table, calcium, barium, and strontium are heavy compared to beryllium and magnesium. for example, which are lighter group 2 hydroxides. Magnesium hydroxide is not soluble, and so it won't actually generate OH minus when you put it in water. But this collection here, they are soluble. And of course, calcium hydroxide, barium hydroxide, and strontium hydroxide, they each carry 2 hydroxides. So they are like H2SO4, which gave 2 hydrogens. Well, these will give 2 hydroxides when they dissolve in water. And just like there are strong and weak acids, there will be strong and weak bases. So they will produce OH minus, just they'll do so in a reaction which reaches equilibrium. Here again we show that equilibrium arrow. So ammonia is one of them. It will react with water and it will actually take the hydrogen away from the water and leave OH minus behind. And so it does generate OH minus in solution. This is a type of reaction that breaks a water oxygen-hydrogen bonds, and we call that a hydrolysis reaction. And here we can see that just like for the weak acids, most weak bases are going to be highly reactant favored. Their K equilibrium constant values will be much less than 1, on the order of 10 to the negative fifth or even smaller. Okay, and that's it for 16.1.